Experiment number one is us trying a PD controller logic to provide the voltage to the motor. And this block diagram over here accurately represents how the PD controller is going to do its job. So let me do some annotations. Okay, so we measure the speed by numerical differentiation, and the desired speed is 12. The difference between 12 and the other speed is this error. And then the proportional derivative controller, PD controller, is going to use this error to calculate V, which is the over and above voltage. Now, why is this called a PD controller? The reason is very simple, because this is a transfer function, Kp plus KdS. And so meaning of the transfer function is that the output V is transfer function multiplied by the error. But we can convert this relationship between E, the error, and the voltage V from Laplace to the time domain. So Kp times E would be Kp times E in the time domain, but Kd times Se is going to be Kd times E dot. So that means the voltage is proportional to the error with a gain Kp and is proportional to the derivative of the error with a gain Kd, and hence this is called the proportional derivative controller. If you look at this transfer function Kp plus Kds, you can rearrange this into some gain multiplied by S plus 0. So basically proportional controller is the controller with 1 0 and gain. You were supposed to design a controller to meet these specifications. Now, these specifications are kind of artificial. They do not come from the customer. We're just trying out things, and we just chose these specifications. But ultimately, the real specifications will come from the customer. So what were our specifications? Settling time should be zero point 0.2 seconds or less, and the zero of the controller, which also is a zero of the closed loop system, should be minus 30. So with these two specifications, we should be able to find the gain and the location of the zero, which is already given actually, is 30. So Z must be equal to 30. And with these specifications, ultimately we'll be able to find the KP and KD gains. And that's exactly what you guys did in the pre-lab. So let's go over the pre-lab real quick, because I have the solutions to the pre-lab made by me. So this right here. So the first step in the discussion in the question was, if you want to find Kp and Kd, you have to find the closed loop transfer function, because ultimately you give a reference command over here and you get an output over here. The relationship between the reference and output is going to be the closed loop system, and the closed loop system is gk forward path divided by 1 plus gk. And so if you do all that math, gk over 1 plus gk, g is equal to kdc over tau s plus 1, and we know the value of kdc is about 1.06, and we know the value of tau for our motor, which is 0.06, and k is kp and kd. So this is what we're going to design today. So we plug all this stuff in, and if you simplify gk over 1 plus gk, this right here is your overall transfer function, the closed loop transfer function from r to y. Okay, and if you look carefully, the top part has 1 0 and the bottom part has 1 pole. So it's 1 0 1 pole system. Okay, and furthermore, the 0 is equal to minus kp over kd. If you put the numerator equal to 0, that's same as 0 of the controller. But the pole is going to be obtained by putting the denominator equal to 0. It's going to be negative of this constant term, divided by this coefficient of s. So that was our second question. Find the closed loop poles, which is going to be negative of this constant term divided by the coefficient of s. So that thing, which is a function of all these constants, is our pole. And settling time is 4 over the pole. Now this formula is not exactly valid for a system with 1 pole and 1 0. It's going to be approximately valid, but we're going to use this formula anyway, and hopefully we'll correct it if needed. Okay, so settling time should be 0.2. So that means the real part of the pole should be 4 over 0.2, which is 20, in at least the magnitude of it. So this number over here should be 20. So negative of this number is the pole, and that pole is minus 20, so that number is 20. So that's one equation we have. And the second thing was the 0 of the closed loop system, which is Kp and Kd. Kp divided by Kd with a negative sign, also the 0 of the controller, that should be 30. So if you rearrange this, that basically means Kp should be 30 times Kd. So these are the two relationships we have involving Kp and Kd, and we can solve these relationships to find the value of Kp and Kd. And now if you plug in the values that tau is 0.06 and KDC is 1.06, we can calculate the value of Kp and Kd, the gains. And those gains will come out to be some numbers, which I will tell you shortly. Okay. Now, um, as mentioned earlier, these these numbers over here, um, the numbers we're going to calculate, they were obtained from this settling time formula, but this settling time formula is not 100% accurate. So we're going to test out this whole thing in MATLAB. So you will do the step response of the closed loop system. And since the step value is not 1, it's 12. So you have to do the 12 multiplied by the closed loop system. If you do the step response of the closed loop system, you will figure out that there is slight difference. So the settling time is about 0.2. It's not terribly far. And at that point in time, you can adjust the gains a little bit until you get 0.2, but I'm not going to do it because it was pretty close to 0.2. So that's all. And by the way, I think I did some calculations a while back, but those numbers I put in the code directly. So we'll take it from there. Otherwise, they are right here. Okay. So KP came out to be 0.566, and then KD came out to be 0.0189 for my tau and KDC, which were for the plant as shown. And if I do the actual step response, you'll notice that the settling time was pretty close to 0.2. So I'm just going to stick to the gains which I just calculated. All right. So let's take these gains and then plug them into our controller and see how that works. Okay, so open the Arduino code, which is right here. So define the variables up top, the setup thing just does its business, set a 0 voltage, and then waits for 3 seconds. You do your disk angle and the previous error business, all done. And then inside the controller, inside the loop function, that's where the magic happens. We first find the disk angle and time, and we calculate the disk speed. And this is where I have already put the value of Kp I calculated and the value of Kd I calculated. This is, by the way, the minimum voltage, and we'll need it too. So minimum voltage will make the motor just move. So what was our PD logic? According to the PG logic, voltage minus the minimum voltage, which means the voltage above and beyond is going to be given by Kp times error plus Kd times the derivative of the error. I'm going to take that minimum voltage on the other side. So that means the voltage given to the motor should be Kp times error, Kd times error derivative plus the minimum voltage. So that right there, that one line is our PD controller. Error is, of course, desired speed minus the disk speed, and the desired speed is defined up someplace to be 12, and the disk speed is calculated right above it. Okay, and the derivative of the error is the current value of the error minus the error in the previous loop divided by current time minus previous time. So that means we have to keep track of the previous error as well. So we have to have an extra variable, and that's a previous error variable along with the previous angle variable. And that previous error was defined to be desired speed minus 0 because the disk speed was originally 0. Okay, so we have an extra variable which we define, and we're gonna calculate the voltage, convert the voltage into the DAC value using the linear relationship, cap the DAC value, and then provide that DAC value to our motor. And then we print the time, speed, and DAC value on the serial monitor for each loop. And this is where we reset all the previous variables, previous disk angle, previous time, and the previous error, which is a newly defined variable, then used to be in the proportional controller code. Okay, this is our code. I am ready to upload this. So let's see, is my Arduino connected? Yes. Turn on the voltage supply, and then let's click on this. And I'm also going to open the serial monitor, and let's see what happens. So this is spinning because there's already existing code up here. And Arduino is still thinking. I think it's going to stop responding. Oh, nice, it's working. Done uploading. Disk has stopped. Hey, did you hear something? The disk is like so jittery. I actually can hear this jittery sound over here. Okay, that's a problem. Anyway, I'm done collecting my data. So now you're gonna take all this data, control it, and save it in the text file, which I already have over here. So this is my text file with the data. And the next step is to run this data through MATLAB. So let's open our MATLAB file, which is right here. In this file, you write down the name of the text file where the data is stored, write down the KP and KD gain you used, and define a transfer function out of them, which KP times SKD. Also define the motor parameters, and find the plant of the motor, define the plant transfer function. And this is our data, by the way. We upload the data. First column divided by 1000 is going to give you time in seconds. Second column was the angular, not position, but angular velocity. And then the next was the DSC value, which we can convert into the voltage if needed. Okay, so then we smooth the speed, and then we simulate using the LSIM command. We do a step response of the closed loop system. Plant times controller transfer function divided by 1 plus plant times controller. So the input to this system is the desired speed. So we actually simulated the theoretical response, and we're also going to plot the actual speed which we obtained from the experiment. So hopefully the theoretical and the other one would not be too far away from each other. Let's have a look, and you'll see the reason why the speed was ever so jittery. Okay, is it busy? Yep. So my computer is slow. Every time it gets busy, I'm like, is it gonna go not responding? Okay, so here is the response. The theoretical response, the green one, is not terribly far away from the experimental response. This is like 5 point something. This is like 4 point something, the speed. But notice one thing, the experimental response is very noisy. And that's a problem with the PD controller used all by itself. And what are the reasons for this noisiness? Well, if you remember, the speed is obtained by differentiating the angle. So whenever you do the derivative, it makes the small errors pop up even more, because how do you do the derivative? It's difference between the speeds divided by difference between the time. Here is your code. This is where you're doing the derivative of the speed. You're doing the time difference. You're differentiating the angle with the time. So if there's a little bit of error in the angle divided by this time difference, which is a couple of milliseconds, that error is going to become really high because you're dividing by a much smaller number. So therefore, even if there was a very little angle error, when you find the disk speed, there is more error in it. But still, it's not too bad. But the proportional controller does even one step further. The proportional controller, so this PD controller, it does the derivative of the error. So angle was a little bit of error. Disk speed is going to have more error because of differentiation, because of division by a small number. And the error derivative is going to have even more error. So the error derivative is a very noisy term. And therefore, the voltage you are giving to the motor is also very noisy as calculated. So that's why the motor speed was so jittery. So that's a problem with the PD controller, that if there is some noise in the sensors, the PD controller is going to amplify the noise. Let's see how to fix that situation by using the controller in the next experiment, which is a PD controller, but with some extra addition. Okay, so let's stop recording.